All right, well, it's a pleasure to have Jennifer Schwarz here from Syracuse. She has, as most of you know, a wide-ranging interest in gene regulation and in actin cytoskeleton and quantum percolation. And she's done a lot of work on jamming, and so she'll talk about disordered mechanical networks from jamming graphs to anisotropic rigidity percolation. Thanks a lot.
Well, I would say probably constraint percolation models, which the jamming people would say has nothing to do with jamming. But anyway, yeah. So I kind of try to carve out my own niche, but it's gotten me in trouble. And I paid the price dearly, I can tell you that much. So I'm going to talk about 3 papers today. I am looking for a pointer.
Yes.
There is, okay, I will use this. Yeah. Great. So 3 papers today, an image from each of those papers. So let's start with something maybe that we can think back to 1864 and the famous Maxwell constraint counting paper, where he was thinking about frameworks, which are really bar joint networks, so sticks that are connected with joints, and the joints can freely rotate. Of course, I just sort of put this image of the Eiffel Tower up there. Of course, the hinges there are not freely jointed. I'm sure they're in concrete and really extra supported, but that's just sort of, let's take our artistic liberty to put that there. But so you might want to consider this sort of as a framework. And so Maxwell was obsessing, pardon?
Sorry, apart from the reinforcement, is it actually rigid by the criteria you're going to tell us about?
Well, that I don't know. I haven't yet done the counting. So that actually I was thinking would be an interesting play to write. If Maxwell met Gustave Eiffel, did they actually meet? And if they had met, maybe it wouldn't have been such a regular structure. Maybe it was, I don't know. Yeah, so I thought about that. So we consider a bar joint network made of n vertices, such as a square. Okay, or a triangle. We'll have some pictures in the next slide. And NF degrees of freedom, okay? And we're going to work for the rest of this talk in, as Bobo did, 2 dimensions. And NC bonds, and we're going to call the Z bracket the average coordination number. Well, for flexible networks, NC must be less than NF. So the number of constraints must be less than degrees of freedom. So maybe this will be boring to some people, but let's just walk through it for a moment. A minimally rigid framework is when the number of degrees of freedom is equal to the number of constraints. And this happens in 2 dimensions. Here are the number of degrees of freedom. So you have 2n in 2 dimensions. Each vertex can move this way or this way. And you subtract off the 3 because you have 3 global degrees of freedom. Translation, everybody translates in the x, everybody translates in the y, everybody rotates. Okay? You set this then equal to the number, instead of the number of constraints, you can also call it the number of bonds. And in terms of the average coordination number, it's average of z times n over 2. Because of the double counting via pairs. And so you get then, if you want to solve for this ZC, this is what Marcus had written down earlier in 2 dimensions. Okay, there's technically this 1 over n correction because you subtract off these 3 global degrees of freedom, but fine. And then, of course, if you have a rigid network, you're over-constrained, and so your number of constraints is greater than your number of degrees of freedom. And so here's a couple of examples. Here, of course, we're all familiar with our drying racks and whatnot, or that you have a square, you can compress it down, just fold it up. Here's another flexible network. This is actually your simplest minimally rigid graph, a triangle. I like triangles. Here's a slightly more complicated minimally rigid graph, and here are 2 examples that are over-constrained. Okay? And so fine. You might think, okay, well, Maxwell's constraint counting is the end of the story. He's brilliant, and so he is brilliant, and so fine. But it turns out that this isostatic condition in large N is a necessary but not sufficient condition for minimal rigidity. Okay, so what happens is this graph satisfies Maxwell constraint counting, but it is not minimally rigid in the sense of this part here can collapse, this right half of the graph. Okay, and so in 1970 or so, Lamont came along, and maybe this has been in the literature some, but he formalized it with something called Lamont's theorem, which is now the statement that a two-dimensional graph with n vertices is minimally rigid if it has, in total, 2n minus 3. Again, the 2 comes from the 2 dimensions, the 3 comes from the 3 global degrees of freedom, and every subgraph contains, with n vertices, contains no more than 2n minus 3 edges. So you have to check everywhere in the graph, and you can't put redundant bonds in. Okay, fine. So this maybe is not a mystery to anyone. This is somewhat obvious. So fine, you could say, from a physicist's perspective, you could ask, well, how does a bar joint system become rigid? Well, you add more bonds, as we know, or increase the density packing fraction if you go back to your jamming system. But here you go from a graph that's flexible to rigid, but via adding more bonds. And so one could, apologies for that, just forget that shear modulus statement. One could say this is a phase transition. Okay? Okay, don't forget that shear modulus. So here, we're going to come back to this in the sense that here is a shear modulus as a function of average coordination number, and this so happens to be for the triangular lattice. And of course, we're going to translate at the end of the day from a physicist's perspective that rigid means you have a non-zero shear modulus. Now, of course, you're thinking about, I'm talking about bar joint networks, and now suddenly how do you measure a shear modulus of a bar joint network? Well, in this particular paper and simulation, in the end of the day, what you do instead of considering bars and joints, you consider springs, because that's similar in the sense that to not change the energy and move the bar joint network around, you need to keep the length of the rod fixed. Similarly with springs, there's energy cost to stretching them or compressing them, so you're changing the length. So basically, putting in energetics into the system in terms of springs is a way to sort of look at mechanics of these disordered mechanical networks. Okay, so so I said, okay, phase transition. Now, for us at the KITP, we might be interested in phase transitions in mechanics. But who else might be interested? Why care? Well, let's just say you have a square lattice. And as we just said, a square lattice, you can collapse it down. Okay? So it's not rigid. And that's also to make a point right here. The average coordination number, well, it's an order case. The average coordination number is 4, right? Which is the isostatic condition in 2 dimensions, but it's not rigid, okay, because of this particular configuration. So you might ask as an engineer, how many crossbars, the Gustave Eiffel could have asked, Maxwell, how many crossbars or next nearest neighbors do I have to put to make this rigid? Now it turns out that a necessary condition is that you have to have at least one next nearest neighbor per column per row. Now it turns out that's necessary but not sufficient. But in any event, these are sort of, from a civil engineering perspective, you could, given the Eiffel Tower picture, you could consider that interesting. Now, here is a picture. Now, I just sort of put it up here. This is from inside a cell. So this is, I'm becoming more and more interested in biology, so I'm going to throw a little biology at you just for the heck of it, so maybe you learn something and walk away. So Maxwell, I'm sure, wasn't necessarily thinking about bar joint networks or spring networks in biology, but it turns out that the cellular cytoskeleton of a cell, like our bones give us support, gives the cell support structurally. The cytoskeleton is a little more interesting because the bones, if you will, the filaments can change shape and cross-link and bind and sever and branch. So in the end of the day, this is inside the cell. These are actin filaments, and this is part of what's called a lamellipodia. And the point is they're sort of bar joint or spring networks inside the cell. And so asking questions about the mechanics of cellular mechanics is also related. And so I'm trying to try to motivate a little more. And if you're interested in robotics, this is something, okay, I assume everyone's seen this movie. This is the movie where, is it playing? Oh, it takes a moment. So we go from frameworks now, a little bit different, to now, if you will, jamming, what Bobo had talked about, where you can go, well, we talked about a phase transition from flexible to rigid through this minimal rigidity point. This can also effectively happen in granular materials. This is this universal robotic gripper, where it's interesting because what happens is you put air. So this actually is made of, inside this vacuum bag is coffee grains. And they let air in. And so if you let air in, the system actually fluidizes. And you suck air out, then it solidifies. And so basically what happens is, I guess in robotics, it's hard to design, if you have a gripper like this, oh, can I pick up this? It's hard. The point is with this universal robotic gripper, if you put this bag down of coffee grains and they're fluid, they kind of fluidize and they move easily over the pen, and then you suck out the air and it solidifies, and then it can easily pull up any kind of shaped object.
I had kids make this and pick up Lego blocks. They were
well, and I guess I won't tell you, well, maybe I should tell you why I'm thinking of this, but yeah, actually someone came up to me and said, babies that are being born, I remember you used to use forceps. Now actually someone has designed something like this where so it's much more gentler on the baby, trying to get the baby out. So you put it around the baby's head, and yeah. Anyway, so lots of different reasons. So I mentioned just this here because we're going to head a little bit toward jamming, but we're not going to quite go there, as you'll see. This is sort of the end game for me, which I don't yet understand. But this is then as the sand grains as a function of packing fraction or density, where they go, as Bobo had talked about, well, in terms of shear jamming, but here now it's and these are frictionless, yes, in this picture, frictionless, changing the packing fraction, which as opposed to keeping the packing fraction fixed at 0 temperature and shearing it yeah, with friction, yes. And of course, Bobo, I guess, in terms of people that are, outside the community, jamming can occur in many different granular. What you mean by granular can depend on system size. So these are colloids, titanium oxide. This is a 1 micron bar. This is foam. This is Gillette shaving foam. This is okay. This is not from the paper. Don't shoot me. But yeah, this is 1 millimeter, and this is of course a picture of M&Ms, which we know the scale of that is about 1 centimeter. And this is actually a picture, so this is from a beautiful review Bobo is on. This is something with, in terms of contact geometry as a function of packing fraction. So this is actually subtracting off that critical ZC. Now it turns out here, so we keep saying ZC is, 4 in 2 dimensions, or it's 4 minus 3 over n. It turns out with friction, so this is, again, these are experiments of friction, as Bobo said, it's not a fictional particle, as Bob likes to say, it's frictional. And so it actually turns out that from the counting you can get Z in general is D plus 1, but fine. So there are also numerical studies of jamming, repulsive soft spheres. So again, for people that maybe are not so familiar.
Can actually be between 3 and 6.
But technically, yes, and depending on how many fully mobilized contacts you have, exactly. So I'm throwing a few things under the rug, but please, this is more an advertisement to come talk to me if you're interested. So this is as Bobo said, for what now it's 1995, 25 or 1995, so almost 20 years. Yes, thanks. That people have been doing the simulations. This is, I guess, started off by Doug and followed by other people. Of course, maybe there are earlier articles as well. This particular potential, where if they don't overlap, 0 energy between them. So Rij is the sum of the radii between the two disks, I and J. And if they do overlap, there's some repulsive potential. And here this is from one of Doug's articles. Pressure is a function of packing fraction, and again, average conductivity is a function of packing fraction. So here, presumably there's some sort of phase transition. Now, why am I talking now about jamming when I started off with rigid bar frameworks and mechanical networks? Well, if you look at this system, there are rigidity aspects. I haven't mentioned the word rigid cluster yet, but I'm going to mention that next. So in terms of, we said about constraint counting, and that's really an aspect of rigidity theory. So we have the the Maxwell counting, as we said. It turns out, though, if you take the system, so here is this, I'm sure Marcus can probably do a much better job of explaining this L star, this isostatic length scale, which diverges as z approaches zc. I guess I should have put, yes, we want z to be greater than zc. Good, that's the right sign. And so the point of this isostatic length scale from this paper, so Mathieu has a nice argument, but what this paper does is it does the following. It takes your packing of disks, okay, and it cuts out a subsystem of some length. So this is maybe L naught, this is L1. It cuts out a subsystem, and it actually computes something called rigid clusters. So a rigid cluster is just sort of what objects, if you think back to the bar joint network, a triangle is your simplest non-trivial rigid cluster. Every bond or every edge is rigid with respect to each other. There's some energy cost. You need to put some energy into, if you think about springs, to deform it. So if you map out the rigid clusters, given the connectivity, so here there are no force information. Sorry, Bubble. If you map out the connectivity and then compute rigid clusters, which I may talk a little bit about, but again, that's sort of technical issues in terms of pebble games and whatnot. I'm happy to talk about that if people want in maybe a more detailed tutorial. But the point is they find a rigid cluster that spans the system. So again, the contact geometry via percolation may span the system, but it's not clear just because you're fully connected that you actually are one fully connected or spanning rigid cluster. So I'll sort of clarify that in a few minutes. But the point is they look for rigid clusters or a rigid cluster that spans. Okay? And they keep cutting smaller and smaller system sizes. And eventually at some system or subsystem size, they find a rigid cluster that does not span. Okay? It's a little, doesn't feel the boundaries. And so what then they say is that length scale upon which you go from spanning rigid cluster to not spanning rigid cluster is this L star. Okay? So that's, it's definitely, it's related. So think. So, I mean, it's not obvious, but the point is they keep, and they have free boundary conditions. They keep cutting out
but
smaller.
The boundary conditions at the boundary are frozen, right?
That's right.
The positions outside that are frozen.
That's right. Yes, they're fixed. Sorry. And the point is that they can go from a spanning, or they find a spanning rigid cluster to something that is isolated. I mean, yeah, it's kind of how that works. It's very strange because actually finding rigid clusters is kind of, it's not to me obvious. Yes, Sid.
Is L star for freestanding system, but if you have a system that's under some kind of loading, that will change? So right now there's no external loading. It's all internal interactions, yes. And one could imagine, well, if you put on more load, then you have more contacts, and then you might change things. Yes, sure.
No, finish.
I'm done.
Now, so in the expression you've written here now, the Z is bigger than the critical.
So they're always working above in the solid phase. And they have a nice graph. I didn't show the data to show this, and they have a nice argument for this based on constraint counting, based on cutting out sizes, cutting out rigid clusters. So I'm not doing justice to this work per se, but I just wanted to tell you that there is a way of looking at from rigidity theory, as we'll see in a moment, jamming.
So you're assuming that some critical exponent is 1.
Well, that's what they're finding, yes. Yeah, and that actually, this nu equals 1 is what Mathieu arrives at as well with the cutting argument. Yeah. So it's kind of I don't want to say, it's arriving at the same result that Mathieu arrives at just by, maybe doing a little more work, but maybe it's a little more, few less assumptions, but good. Okay. So the point is there's this sort of jamming stuff, and there's the particles move around and change connectivity, which makes it a really tough problem.
And then there's kind of the rigidity theory, the spring networks, the bar joint networks, which is actually a much easier problem because at the end of the day, the connectivity is fixed. Yes?
No, so I correct me if I'm wrong, but I mean the argument that Matthew Weir had presented earlier was looking at approaching the jamming point from below.
No, it's always
No,
from below.
no. So basically, you take a region.
You have an energy cut, so it's always compressed. Right?
So you're balancing in the end of the day. Again, Marcus, do this justice.
Over compressed to unjamming. It's always the unjamming condition, not the jamming.
You know, you're comparing. So you have a system where you do make a cut. You do cut out a boundary, but but before the cut, you've got z minus. Okay, let's do this. Times L to the D, sort of constraints, if you will, and you balance this against the number of soft modes you generate, which scale as the boundary. So this is L. This is now some boundary system. You know, is L to the D minus 1. And so there you can get this. Then you get a simple, the previous page. So that's sort of the Weir cutting argument where you cut out.
Just want to mention there are some interesting recent stuff from Tom Lubensky, right, on looking at isostatic lattices.
Yes.
And there, the exponent actually has logarithmic corrections here. It's not one.
Right. I mean,
And
so
it also depends on the lattice. So it's not always in D minus ZC to something.
yeah, I mean, it's a different system. And again, so these disordered networks that we're going to talk about, yes, so one case is, as we said, that case of the square lattice. So it's isostatic, if you will. And then if you add next nearest neighbor bonds, you can ask, is that kind of like a jamming transition? And certainly there are some similarities and some differences. Exactly. So, you know, the name of the game for me is trying to extend rigidity theory to sort of more resemble jamming a little bit, trying to close the gap between the two. And so it's a little bit hard, though, because jamming systems do not have fixed connectivity. And I guess I should put here, we're having purely repulsive interactions. So I should mention that. So in the case of purely repulsive interactions, of course, you know, people, we have to have not just the global constraint of isostaticity or Lamanness in 2 dimensions for necessary and sufficient. The particles, each particle, you know, these 2 examples, or this center particle is not mechanically stable in the presence of purely repulsive forces. However, this configuration is. So it turns out that that property of local mechanical stability can be built in the context of each particle. If you consider that as a vertex in your graph, must be surrounded by at least 3 of its neighbors in a triangle. Okay? And that's your principle of local mechanical stability. And so the point is, as well, can we then combine and maybe, you know, again, sort of teasing out what are the effects of isostaticity or minimal rigidity, and what are the effects of local mechanical stability? There's sort of 2 constraints, one local and one global, if you will, or non-local. And so the question is, you know, if we combine the 2 to make the graphs or the rigidity theory a little bit more like the jamming systems in the sense of you also have to have this local mechanical stability constraint, then what you arrive at is what I'm calling a jamming graph. And I guess I should also state here that in the end, if we want to map this to particles, the Lamand graphs must be planar, meaning because each edge is 2 particle contacts. So it wouldn't, you know, how do you have a cross? What does a cross mean in terms of particle contact? So basically, this is the jamming graph. This is an example of it, a planar Lamand graph plus the counterbalancing criterion. Now, interestingly enough, you know, people might say, oh, well, you know, I'm talking about minimal rigidity, and that's sort of a global constraint in the sense of it's a constraint on the average coordination number of this graph, and there's certain very particular properties of the subgraphs and whatnot. But it turns out that you can generate, starting from a Lamand graph, again, triangle being the simplest one, you can generate using local rules or continue to generate a Lamand graph. And these are called actually Hennenberg steps. And these are actually simple local rules where if you have a Hennenberg or Lamand graph And what you do, so here's my triangle, I add 2 edges and connect it with the vertex. If I do that, it turns out you can show by induction that I propagate the Lamanness, okay, the minimal rigidity. So when I say Lamann, sorry, I mean minimal rigidity. That wasn't clear.
With this condition of local stability?
No. No, that's a little bit harder. So that's where all the work comes into building the algorithm, because this algorithm is actually very easy to code, but then sort of enforcing the local is a little more tricky. And there's also another one you can do called type 2, where you start with a triangle, you add a vertex, then you add 3 edges, and those 3 edges are from 3 prior vertices. And then what you have to do is you have to remove one edge connecting any edge connecting those 3 vertices. Just remove one edge connecting those 3 vertices, okay? And then what ends up happening is you, again, propagate the Lamanness. So it's very easy from this local rule algorithm to generate a planar Lamann graph. It's not so easy to generate a jamming graph, but not too hard. But in any event, you have fun creating an algorithm, sort of. But algorithms are okay, but I'm more interested in results. So now we have this jamming graph, and so we ask, all right, let's study this object a little.
So the vertices are always the location of
a particle, ultimately, yeah. Now here, there's the algorithm. You put the vertices, uniformly distributed, whatnot, and I'll mention at the end about the end of this part just a little bit about particles, but to sort of reverse engineer to go from again frictionless to go back to disks, if you will, 2-dimension. But there's some interesting stuff here. You take these 2 jamming graphs, and in this case, now, so what do you mean by minimally rigid? I mean, so here, this color is all one rigid cluster. So it doesn't mean about connectivity now. Okay, I keep obsessing about that, but maybe you guys, in terms of, connected clusters from just regular percolation theory. This is one rigid cluster. This is one rigid cluster. Now, the statement about minimal rigidity from a physics standpoint really is, mathematics standpoint, you remove an edge. What happens when you remove an edge is you must have at least 2 rigid clusters. You must have at least 2 rigid clusters. So the graph, if I'm now color-coded according to rigid clusters, so does everyone know what I mean by rigid cluster? I mean, I stated it before, but just sort of bonds that are rigid with respect to each other. So if I remove, let's see, I forget which bond is removed in this graph. I'll show you. This one. So if this bond was removed, it turns out I get this profile of rigid clusters. Okay? These black ones are isolated bonds, meaning bonds that are not rigid with respect to any of the other bonds. Okay? Here's a couple of triangles. Notice you can never have a rigid cluster of size 4, the bond length 4, because that would be a square, and a square is not rigid. So there's certain shapes that obviously are excluded. But here you have a case where there's lots of smallish rigid clusters. And I say that very loosely. And then here's a case where we've removed this bond between site 30 and 12, and you still have the system as somewhat connected in a rigid sense. A rigid cluster that kind of the scales of the system size, and then here's a small triangle, and here, of course, are some isolated ones. So there's kind of 2 sort of different pictures, and then you say, well, okay, these are just 2 examples, and so let's then do some statistics, and you say, okay, well, on this x-axis is the rigid cluster size S. Here's the probability of having that rigid cluster size, and these are for different vertice numbers, so increasingly larger system. And what happens is you do, on a log-log scale, get somewhat of a broadish distribution for smaller rigid clusters, but you do have this characteristic peak at larger system sizes that's emerging. So you kind of have this funky, two-type behavior going on here.
Can I ask a question before we move on?
Yes.
You define the rigid cluster size is by the linear span, the size, basically?
No, I define it as the number of bonds. That's an excellent question.
That's
yes.
the first question.
So
question.
Triangle would be a size 3.
Okay. All right. Second thing is you define, for me, if I follow your argument, triangle in 2D is a rigid, locally rigid structure. If I continue build my network based on these triangles, eventually I can build an over-constrained network.
Yes.
But
I mean,
I'm going to over-constrain it. Now the question, could I ask this question maybe following your algorithm? If I continue this, I actually go through the redundancy. So now the question I face is that if I have to reduce the redundancy, right? Because on different scales, you have a different triangles you can create.
right. So here's an example. And maybe this is what you sort of have now two triangles, but they are sharing an edge. So that in that way, you would preserve the Lemon aspect of it. But there are other ways that maybe.
If you share a vertex, you don't build.
That's right.
Right.
So meaning.
You have certain rules, right?
Yes, there are certain rules.
But again, if I follow the rule, I share the edge, I continue to build it.
Mm-hmm.
Eventually, I can build a larger.
Right. So the next one would be add a vertex here, and so yes, these triangles are always as long as you're.
The interesting thing coming here, if I follow this, I'm thinking that if I build continuous spanner cluster, eventually I have a scale issue. I can take some small bonds off. I have a larger triangle.
Sure.
Right?
Sure.
That is stable on the larger scale.
That's right. So if we put two bonds here, we create now 3 triangles, each
well,
two.
somewhere you find the bigger ones.
Somewhere, okay.
Well, you can, because all the dots, right? You can create another triangle.
But the dots will not be connected.
You can connect it.
So, Dr. Lee, so you're saying you want to generate basically out of a bunch of triangles a minimally rigid structure, but somehow that can become over-constrained?
Right. I don't need the local stability.
Oh, no, you don't need local stability for Lemanness. Oh, no. That's an added input. Yeah, so that's a good point. So Lemanness is just, it's something that in rigid, bar networks, because the connectivity stays fixed, you need. The property of local mechanical stability is just thinking towards the vertices being like particles that can move in and out of contact with each other. And so in that way, local mechanical stability is a separate issue. And so, yeah. So in the end of the day, I want to sort of tune knobs where I sort of maybe turn off the Lemanness, like by adding extra bonds and play games and keep the local mechanical stability, or turn off the local mechanical stability.
For example, the one in the middle, basically you have 3 triangles, but once I build a large cluster.
Oh, sorry, that's not. Yeah, I'm sorry. Yeah, this is just as. Yeah. So.
I can get rid of the one in the middle. I create another bigger triangle. That's
okay.
What happens to that point then?
Well, it's not necessary. You don't need it.
The point is not necessary?
Well, the vertex is not necessary. Why do you need it in terms of the system stability? I don't need that, right? It's actually become some sort of a scale invariant problem embedded into this problem.
Well, I want to keep this here because I want to say it's a particle. And so basically I want, this plot is to be thought of, this figure, as,
Right?
I mean.
No, but I think what Mo is saying is that if I was looking at a network on a larger scale, if I remove that particle, I would still have rigidity.
Yeah, I still have a rigidity on different scale.
No, because if you're at minimal rigidity, and you remove a particle, you remove edges, then you're going to definitely become flexible.
No, for
big reason that's all the grades.
Not for the one in the middle.
I guess these sort of dotted lines are not to be thought of as edges. The dotted lines are not to be thought of as edges. They're just to be showing you you're enclosing this point in a triangle.
I guess you can define your problem as nearest neighbor.
Yeah, I mean, that's right. Local mechanical stability is a nearest neighbor thing. That's totally correct. So you have 2 different length scales going on in the problem. You have the local aspect of it and then the global. I agree with you. And one doesn't necessarily hinge on the other, depend on the other. Yeah. So, okay, good. Let's just, so please. So there's also other games you can play where, as Dr. Lee just brought up, you can actually add bonds. When you add bonds, you become over-constrained. And so then you're in the rigid regime, okay? And so you can play the game then of adding bonds and then deleting some. And what ends up happening is, if you delete a couple, there appears to be this gap in the rigid cluster size distribution that closes up after, say, in this case, adding 8 bonds, deleting 2, and now deleting a third. The gap closes up. So one can define this gap, assuming the rigid cluster size is compact, as some length scale, and then via some scaling arguments and some data collapses, you can get, now this is a totally different nu than the 1 equals 1 before, but one arrives at an exponent of a third, at least via best fit in terms of best scaling collapse, I should say. So it turns out to be some sort of perhaps new exponent associated with this characteristic size of adding extra bonds, then trying to fluidize, and somehow having a rigid cluster, a gap in the rigid cluster size distribution that then closes after deleting, say, one further bond. So there's all sorts of games one can play with these rigid clusters. This thing, so in terms of this aspect, this is, I should say, this stuff here. I mean, it's really interesting in the sense of one could ask, does this type of example survive in the infinite system limit? Now, if you talk to a mathematician, they haven't been able to prove, even in the random graph case, if you delete an edge, when you're at minimal rigidity and you delete an edge, does the system always break up into lots of little rigid clusters in terms of that's how does it fluidize? Take this really hokey example. I mean, mathematicians are good at coming up with hokey examples, but at least it illustrates a concept. Take this graph. Again, it's pathological, but let's just consider it. Okay? So a bunch of triangles that are, what would you call this? Sandwiched in between, and here is a final edge. If you remove this edge, then everybody becomes hinges. Hinges, bonds, rigid cluster size 2 is not a rigid cluster. Everybody become hinges. So basically, the whole system breaks up into rigid clusters of size 2. Okay, depending on how you could go ad infinitum, these triangles. However, if you keep this bond and delete this bond, the rest of the graph remains intact. You just have this one extra rigid cluster of size 1 bond emerging. So, there are examples out there, very, odd, but, maybe this sort of two case scenario might survive. Or maybe this doesn't survive and you always break up into small rigid clusters. So there's lots of, this is just the beginning, this paper. Some of the work, so as Bobo mentioned, sort of creating an algorithm to generate the jamming graph. That's part of the paper if you want to look at. And then this sort of finding of a jamming graph, which is at the threshold of marginal stability. If you remove one bond, you fluidize. How do you fluidize in terms of breaking up into rigid clusters? There's some interesting statistics there. Perhaps, since rigidity theory has been applied to, explain this exponent of, 1, a la the isostatic length scale, maybe there are sort of other, certainly exponents in the jamming systems that rigidity theory finds that maybe can show up in the jamming systems if you as you apply rigidity theory to them. And now one asks, so going to what Professor Shastri mentioned, we have this graph and these points and these edges. Can you reverse engineer, put particles in? And there's some hope that maybe yes, because there's something called a circle packing theorem, which states that any simple planar graph, so simple in 2 dimensions, which means you don't have an edge coming back on itself in terms of the vertex, you can find a circle packing for. So, so maybe, that can be done. So we might be able to, put in particles, and we can say, oh, this is our definition of jamming that doesn't necessarily depend on protocol, and, maybe, as Professor Shastri's pointed out, maybe there isn't, there's a range of phi c's, maybe, all these different questions. I'm sort of bypassing that. Oops, sorry. All right. And maybe sort of going at it from a standpoint of let's start from minimal rigidity, and let's try to put in particles, and maybe there's not, for different polydispersities. You can find all sorts of different packings.
So these are real graphs. The lengths don't matter, right?
The lengths in some sense don't matter. That's right. And so what ends up happening with the circle packing theorem, you can perform conformal transformations, and so lengths can change. Now the thing is that if you want to preserve local mechanical stability, you have to make sure angles don't change so that your triangles sort of. But that should be okay. So I'm hopeful it can be done, but this is all in that, so not trivial. And then one could also ask about sequences of moves to get back to minimal rigidity. So the really interesting thing is that, okay, if I have this plot here, I mean, it's all, if I have this plot, and I say, okay, I've removed this edge. I want to get back to minimum rigidity. So, okay, yes, one way I can do it is putting the edge back in where it was. If I want to think of, well, maybe I want to put a different edge in. Okay, again, there's local mechanical stability issues too, but what happens is if you put an edge anywhere between two disjoint rigid clusters, you get back to minimal rigidity. So because that makes sense, because of course you need to add one more bond, because you removed a bond to get back to rigidity, and you don't want the bond to be redundant. So that all makes sense. So the point is when the system, a jamming system is kind of searching through configurations, if you shrunk a particle, maybe there are moves that are such that it's trying to find back, to get back. I want to become one rigid cluster again. And of course, enforce local mechanical stability at the same time. How do you do that? So one can sort of play some games with these graphs and come up with, yes, it would be rule-based and whatnot, but try to define sequences of edge deletions and additions that maybe could be searched for in the jamming simulations. And there's sort of people have been studying contact changes near jamming, and there's a recent paper that says, yeah, we don't really understand how the contact changes work. Well, my maybe shtick might be, well, maybe if you look at rigid clusters that are sort of dynamically forming as the contacts are, maybe one would get some insight. So that's what I'm going to try to do. So really quickly then, I won't be too much longer. So I talked about rigidity theory. Rigidity percolation is this, maybe, I don't know, you could say it's a subset of rigidity theory, I don't know. But here now we actually go to spring networks. Here is your energy. Basically, there's some energy cost for changing the lengths from some equilibrium length. Here is again that shear modulus as a function of connectivity, average connectivity. This is divided by 6 because this simulation is for a triangular lattice, I should say. Now, what I was going to try to go into, but I've decided, let's not do it. Effective medium theory. Now, this here are data points from a simulation. But you can actually, there's a, if you will, mean field theory for calculating this G as a function of what in the end of the day we'll call P, occupation probability. This G is equal to this square root of 3 over 4 alpha m, mu m, sorry. So this here is what's called some effective spring constant. Okay, so I guess, and here you notice that it's linear. Oops, so this here is P. This is P as well. I'll just write this. Okay, so these are the simulations, 0 and very linear. This, it turns out, if I plotted the theory, I have another graph we'll see in a few minutes. Plotted the theory, it's lies very much close to the simulations. Of course, as we said, or as I mentioned, which I won't explain why effective mean theory is another way of saying mean field theory. And one might say, why does mean field theory work so well? Now, that's a big question, and it seems to work well in jamming as well. So I won't talk about percolation, since you guys seem to know about that already. So, how can we go beyond? So a mean field, well, I should say, maybe I should have phrased this question a little differently. In this case, it's linear springs, all right? And I guess what I'll say is I'm going to skip this. What happens if we want to construct an effective medium theory with angular springs? What do I mean by angular springs? I mean linear springs are a 2-point interaction, which we saw in the picture. Okay, so these are my 2 points. Okay, an angular spring would be, you have a spring here. So an angular spring, this type of effect. So you have another energetic contribution as well. So you don't just have the two, linear springs in series. You've got this third angular spring contribution. And I guess maybe in the interest of time, I won't say, why do you want to include angular springs? Well, and I won't show the cell stuff because I guess maybe, yeah. It turns out that, of course, when you include angular springs, you're including bending energy. Okay, and these actin filaments that I mentioned inside the cell, the actin inside the skeleton, they happen to be semi-flexible polymers, so there's some, bending cost to bending them. And so one might want an effective medium theory or a mean field theory of these disordered spring networks that include bending or include angular springs. And I should say, and so here's now the energetic. So you've got, of course, the linear spring contribution. You have an angular spring contribution that's collinear along what we would call filaments, okay, or polymers. So this is one polymer. And let's say we have also an angular spring between these two polymers. It would be actually angle-constraining crosslinkers. It turns out that, so when we talked about the spring networks, usually you assume a freely rotating crosslink. But one can ask, well, what happens if you put in an angle-constraining crosslinker, if you will, between two spring, okay, I'll call them filaments, polymers, springs, now all the same thing. So you have two types of bending, if you will. Okay. Now this problem, at least this problem, this plus this, had been out there since 1985. Michael Thorpe, he's a great scientist. He had done the effective medium theory for linear springs, but he had a 1986 paper that said, well, we tried to do some effective medium theory with bending, say with this term, but our effective medium theory gave us the onset of rigidity is 1/3. Turns out for triangular lattice, the connectivity percolation threshold is like 0.347. It's 2 times sine pi over 18. I'll show that in a minute. In any event, they knew their theory was wrong. So they didn't show the theory because it was wrong. They showed simulations. So it turns out that the problem has been long-standing. And I guess I won't say that, well, okay, so with Momita Das and Dave Quint, I think we've found a good effective medium theory for including bending, okay? And here I've plotted the shear modulus as a function of now occupation probability, which is just this. Here I talked about average connectivity initially, for different, if you will, bending constants. Okay, this is the case with bending along filaments. So this is EM, this is the theory, this is the simulation. Now I'll show a plot later where I actually plot the two on top of one another. You'll see that they don't quite agree, but fine. This is the theory, this is the simulation for when you have angular constraining crosslinkers, and this is a theory when you have both. So you have these both types of bending turn on. Okay, so here are the simulations, here are the theory. Now, we get good agreement, reasonable agreement, I should say. Here's sort of an illustration of the network. So again, it's a triangular lattice. So all these things triangular. Here are the angle constraining crosslinkers. Here is the rigidity percolation threshold as a function of the occupation of angle constraining crosslinks. So these red guys. And one is in the case of not having bending along filaments. The other is bending along filaments. So if I have bending along filaments, it turns out that if I have as many angle constraining crosslinkers as possible and angular springs along filaments as possible, my threshold for rigidity is actually goes down to PC, meaning connectivity threshold. So connectivity of ordinary percolation, you're just searching for connected clusters, okay? And so this particular number is for a triangular lattice bond percolation. You have a spanning cluster at this point. The rigidity percolation, actually for linear springs, is about 2/3, if you notice the graph, meaning you have to have a lot more bonds beyond connectivity percolation to be rigid. Well, that's with just linear springs. Of course, as you put in angular springs, you put in more constraints, so you eventually lower it down to the lowest it can be, connectivity percolation. So there was actually an argument at PRL by Cantor and Weber in maybe 1986 arguing for this, but now we have the calculational machinery to know it. So we can sort of turn the crank and be the monkey. Before sort of arguments would tell you yes, but fine. And I should also say that, okay, so in the interest of the cell people, we sort of motivated, again, this model via semi-flexible polymers a la actin filaments that have freely rotating and angle crustating crosslinkers. So we could motivate sort of the presence of angle crustating crosslinkers biologically is to basically then become rigid with the minimal amount of actin. Okay, so that the cell could easily become rigid because you only have a finite amount of actin in your system, and as the cell moves, it needs to break up its actin and remodel and whatnot. So you don't want to be too over-constrained because then you're basically spending too much money, becoming rigid. You're wasting material. And then there's some other interesting stuff where, of course, if you're near the transition and you add a little more angle crustating crosslinkers, you get a large effect increase in the shear modulus. So you have some cooperative effect. So there's all sorts of interesting things here. I should say that while we work on this paper, I should say that here is a theory, another effective medium theory that analyzes just bending along filaments, so no angle crustating crosslinkers. So our theory is more general. Here is a Nature Phys paper. They have a different effective medium theory, and notice that their effective medium theory, the threshold is much higher than this is our effective medium theory. And of course, our theory is more general. So it's kind of this theory versus our theory, and I should say this paper has now 72 citations. We only have about 10, but I guess maybe the more I talk about it, the more people will know about it. Tom does have a later paper invoking our methods, so I will just say that much. Okay, and then I'll just stop here and say, in addition to including bending, now we can do that. This is maybe more of a drier result. You can then look at effects of anisotropy in these spring models. Now, first we just started with linear springs and put in anisotropy, and you can then, using this effective medium theory, calculate again shear modulus as a function of now py. So we call this. So you have two independent occupation probabilities, if you will. You tune them independently. Here we have px. It could be different than py. And the reason, again, the motivation is ultimately in the actin cytoskeleton and lamellipodia. Actually, there's a bit of alignment, some alignment in the filament. So there is underlying anisotropy in the spring network of the actin cytoskeleton in some cases. And so in any event, I guess I didn't show the other plot of. It turns out that you can tune. So here, notice that for these are different values of px as g as a function of py. You can tune where the onset of the transition occurs. So not only putting in angle constraining crosslinkers, you can, for shift the constraint, shift the condition. If you have two independent occupation probabilities, sort of like a Z1 and a Z2, you can then tune the position of the transition. So it turns out that unlike in just the pure linear case with the isotropic linear springs, where it's linear here, there's a little bit of curvature. And there's some other interesting limits when you have px is equal to 1, and then you start to turn on py. There's some discontinuity in the bulk, but not in the shear. So there's some interesting things here. But it's a little more of a more drier stuff in the sense of implications. Well, actually dating back to Brooks-Harris and whatnot and splay rigidity, which I guess I won't talk about. But if you're really interested in talking to me about algorithm for how to find rigid clusters out of the Pebble game, anything about Lemon graphs, anything about effective medium theory, tutorial on a little effective medium theory, I could give anything you want to talk to me about. And then, if you have ideas about, using this new jamming graph to do certain crazy things with, I'm certainly, willing to talk with you. Fine. Okay.
Yeah.
I was going to ask a stupid question.
There's no stupid question.
In glass theory, one of the things that people talk about, especially the Corning group, about rigidity percolation. Do you make any contact with their concept there? And let me make another remark, is that it sounds fascinating to me, but I've never seen them think about how rigidity percolation might introduce sort of glassy length scales that might diverge at glass transitions. What can you tell us about that?
Boy. Well, what I can refer you to Mike Thorpe. I mean, Mike Thorpe has thought a lot about glasses and amorphous solids as well. Whether he's talked with the Corning people. Actually, the funny thing is, I live 45 minutes away from Corning, so maybe I should go talk to some of these people. So yeah, Jim, I don't really, I don't know what sort of approaches they're using. I mean, I should really try to become more familiar with that. I think that's actually a good idea. So I'll
If you can just give me any clues at any time.
Okay.
Much appreciated.
My question is first, I have two questions. First one is related to this avalanche. So suppose I have a jam with a minimal stability network, rigidity network. What happens if you gradually taking the bonds off? Do you observe the avalanche behavior or the marginal?
Yeah, I mean, I can't in this graph as formulated, because it's really just kind of a static graph, and you remove a bond and you break up the rigid clusters. I remove another bond, and then I'll of course make even more rigid clusters. So as I keep removing bonds, I'll keep making more and more smaller rigid clusters. So the system will eventually break up into presumably all black, all bonds that are not.
But you could ask how many bonds you had to do to
Yeah,
get it down to
that's
just
actually a good
one.
idea. Yeah. So I could ask, as a function of deleting those edges, what is my rigid cluster size entering? That would be like your avalanche size. Ah, that's an excellent idea. Yeah. Okay, very good. Yeah. So maybe we should talk about that.
Second one, thinking actually this rigid bond model you presented here is actually nearest neighbor model. This has been sort of the thought for a long time in crystallography field, because if you construct the FCC lattice or BCC lattice, for example, you put only the rigid bond, they are not actually stable. They collapse. The BCC will collapse. It has been long known in this field, but one way to get rid of it is actually you actually did by putting you put the bond angular dependence.
Yes. Then you can straighten the
in the
system.
other community, what people did was they actually extend the bond lengths. Instead of first neighbor, you go to second neighbor. If you actually on top of I was thinking if I put another network, instead of looking at just the nearest neighbor bond, I actually put the second.
The next nearest neighbor, right?
And then I automatically introduce the bond angular term.
Yeah.
Without complicating your analysis, because you put the theta in, make your life a lot more difficult.
Right. Okay, sorry. So then the comment
So you have a two linear bond model.
Yeah.
They are interpenetrating. I can create a random bond model with two different landscapes.
I'm slightly confused. What is nearest neighbor and next nearest neighbor?
Well, because he has hinges, right? He has hinges. He can.
Yeah, but how do I define nearest and next nearest?
I mean, with a hinge is a three-body interaction. So.
Right, but you remember your spring model, right? You only connect the nearest neighbor.
Right, the initial spring
nearest
model.
and next nearest.
It's just distance in the next neighbor.
No, but it's a graph.
It's
There's
a
no
graph.
distance.
You can find your neighbors.
Okay.
You connect one with the neighbor. The rest could be defined. You can find the next neighbor. You have two types of springs: spring 1, T1, and T2.
Okay, I see. So you want to put two different spring types.
Yes.
You could certainly, actually, that's been is an effective medium theory for this case where you do square, but then you add next nearest neighbor. So you have spring constants, maybe K1, K1 for this, but then of course this is not rigid, as we said. You have to add. So there is a paper.
Exactly. Yes.
There is a paper,
Yes.
1987 or so, where they have an effect, and this is K2.
Yeah.
And have an effective medium theory of that too. Oh, I see. So you're saying do that instead of put angular springs, and that would be easier.
Analytically than put the angular term.
Yeah. But the thing is, this theory actually. So the results are different than this. There's interesting stuff here where you've got bending dominated and stretching dominated. Here's some sort of bend stretch coupled mode. If you do this calculation,
it really just kind of stays more linear. The G is a function of P. I mean, you don't get as interesting effects because, you know, sort of the bending, this here is not really introducing bending per se, because it's still, it's sort of two lattices on top of one another.
What is your
superimposed.
Poisson's ratio, by the way?
Oh, I think it's a half. It's a half.
Yeah, if you have
Yeah.
a rigid lattice, it's 1/2. But
Yeah.
if you put this model,
Yeah, maybe,
you
yeah.
actually change the Poisson's ratio. Also.
Yeah, for the standard triangular, it's a
So-
half, but this, I don't know. So I have to look at that paper again. Yeah, I mean,
Okay.
it generates different results
Okay.
qualitatively than this. I will say that much. And I will try to think a little more about physically why that's so.
Is there a difference between, so for, I mean, simple-mindedly, any angular constraint I want to impose, I can think of doing that by introducing a distance constraint, right?
Okay.
Similarly as spring. So why is this going to be different from?
Yeah, and that's why I'm struggling right now. I'm just in terms of the actual paper, you know, what I see as a function of G as a function of P, I don't remember seeing something as sort of interestingly nonlinear as that. But you're right. In some sense, you would think that's similar, as Dr. Lee pointed out, to the angular case. But I'll think about it and see how different or similar they are. But I agree, there should be some similarities. You should lower the piece, the PR and whatnot. Sid?
Yeah, we keep this graph on the left for now, and then you had a previous graph, which you showed earlier about G versus Z, average value Z.
Yes, sorry, again, so
Both.
so that's, and this is P, this axis is P.
Okay, so that's how you will reconcile these two graphs. You have a sort of a very abrupt behavior, change behavior.
This is 0, so I should say this mu is this value for P greater than PR. So it's 0 otherwise, sorry.
Yeah, so that's really interesting. And then if you go back to the one that we came from, yeah, right there. So you have now two abrupt changes. We have one initially. You were just telling us has to do with angular, and then the other one stretching. So
It's probably maybe a crossover. Yeah, it's probably a
We're
crossover.
looking at a crossover in the first case, and then we're looking at multi-stage response
Yes.
because you have now different degrees of freedom.
That's right.
The angular
Yeah.
freedom versus
Right.
stretching.
Right.
So since you have the simulation, can you really identify what's going on so we can actually have some sort of local detail?
Yeah. So if you look at something called a non-affine parameter, you can see, which is sort of if you shear it, you know, if you look at the displacements that are not along the direction of shear, you have kind of a peak in this non-affine parameter around here, and you also have a peak near the P of 2/3, which is just the linear spring. So you kind of see evidence, vestiges of the linear spring transition in this graph as well.
My question to you is, for effective medium theory, is it a really truly mean field? Does it have tuning parameters? Does it have tweaking parameters? Because it seems to me you're not going to get this without some tweaking.
There are no tuning parameters, and it's actually, it's not even a controlled really approximation. You just assume, you state that the average in the fluctuations, you demand it to be 0. So that's why it's mean field in the sense of you're averaging out the fluctuations in the springs.
So you're saying effective medium theory is truly a mean field theory, strictly.
But yeah, by construction.
Okay, I see.
Oh, yes, sir.
So has anyone constructed the graphs from jammed packets and seen if they have any of the characteristics? So, because it's just constructing those graphs, right?
That's right, yeah. I haven't really talked to, actually, I could run the simulations too, and that's sort of,
Just take code simulations and put bonds between the particles.
yeah, and check to see if this connectivity, right, these graphs have the same statistics as whatnot, yes. So that's sort of what I'm hoping to maybe collaborate with someone with, because I only have so much person power and so much, yeah, and I'm not, I'm not a
the simulation. Right?
yeah, I mean, it's, right, so it's, I don't have sort of a computational
So am I
power
right?
do
All you
that,
have to do is just
yeah.
take, just
it would be an
draw
obvious sort of
connectivity, right?
test.
The next question to that is for looking at the kind of shear jam structures that Paul was talking about. Do you see, will this analysis, or do you expect this analysis to tell you something new and interesting?
Okay, so bubbles analysis is really more analyzing the force chains. In these jamming graphs, there's no force information, though one can ask, I think, one of the questions if you're thinking about putting weights on the edges, and then you have to, those are weights or forces.
No, not if you have tangential force.
Not if you have to, frictionless, yes. I'm always talking about the fictional particles, yes, for me. Though I am, I will make some statements about friction soon, so maybe you'll hear from me about friction in terms of pebble game. The shear jam states, I'm not, so bubbles kind of thing is that we shouldn't be looking in configuration space. And this is position space. We should really be looking in force space. And I think clearly when you have friction and this indeterminacy, that maybe that is indeed, the way to go. Maybe I'm just, I want to say slow. I'm still thinking in position space. I haven't gotten up to bubble speed yet. So these graphs are in position space. That the polygons and all these beautiful tilings in force space. Again, rigid clusters is all just about connectivity. You don't need any force information. So I'm not sure there's a relation, but maybe I could try to think about it more. But these are good questions that gets me thinking.
One way to simply connect, which in my mind, simply connect what you're telling us and what Boo was telling us this morning is that she was talking about viscosity. Right, she was talking about viscosity.
Or shear modulus.
Under shear, right? Now, the viscosity, as she pointed out already, is shear modulus times relaxation time. So there's a natural connection. What you're telling us is the shear modulus, the G.
Yes.
Right, so you may not have, but you could be doing your calculation, rigidity, behavior under deformation. At the moment, you haven't done any deformation. So you could
that's true, and that's, yes.
In fact, it would be interesting to see how these moduli change under shear. Because basically,
so as you shear it more and compress it more, you generate more contacts. I think then you become even more over-constrained, and then be all one rigid cluster again. So maybe that wouldn't be as interesting. But
that's not the question, right? The question is if you start from a non-rigid state, and if you shear it, can you get rigid?
Exactly.
Right. For example, but
that was at least what.
Even the bigger picture is that if you imagine what everybody's talking about, potential energy landscape. Okay, you are in some sense, let's say, exploring potential energy landscape. But if you were to put a shear on that system, the simplest way to think of it, you're actually tilting the landscape. That's what external shear does for you. So you're biasing the system, depending which direction you want to shear. You can bias the potential energy landscape. So in both cases, you're examining the roughness of the potential energy landscape. At least you have a handle. But by not looking at external driving force, you will tilt the potential energy landscape set whatever you start out to be.
But I would think that all of Jen's rigid clusters, when they become rigid, behave like elastic materials. They have well-defined shear moduli. So I don't think she needs to recalculate the shear modulus under shear because there's linear response at some
This
level.
is for what now?
For her rigid clusters, like at least if I think about percolation, rigidity percolation, etc. They become elastic.
Spring network.
They have response that's like linear
Well, the
response.
bending
There's a shear
is
modulus.
linear.
If I define a shear modulus, I'm assuming linear response, right?
But you can go beyond the linear
Of course,
regime by pushing hard,
Of course.
right?
Of course. But
Yeah, sure. Oh, with the spring network, certainly I can, there's lots of fun things to do there. Maybe, yes. In terms of not just small amounts of strain, but going into a nonlinear, large amounts of strain. Oh yeah, in the simulations definitely, there's all sorts of probably interesting nonlinear effects. And in the actin cytoskeleton, you have cross-linking unbinding as well, so you have plasticity as well. And so above a threshold of stress, maybe the cross-linkers unbind. And so there's all sorts of interesting things in the spring networks under shear and compression at larger strains that, yes, we need to investigate. Yes, the effective median theory is only applies to small, small deformations of the linear regime. I see your total, yes. But a nonlinear effective median theory, actually there's work by McIntosh and Scheinman that sort of do some extension there, and I'm looking into that. They've done it for linear springs. The question is, can you extend that to bending as well? So, that's sort of an obvious question that, I'm a little bit, you don't want to step on too many, everybody's working on things and you want to try to if that's sort of the obvious route, sometimes I say I don't want to go on that obvious route because then other people are, But anyway, I'm sort of, competing against Levensky and McIntosh is not, a trivial thing. So, yeah. So anyway, but yeah, those are good points, and they should be done. Whether they're by me or Levensky, I don't know.
All right. If there are no more questions, let's thank her again.